Yeah, so thanks everybody for coming to the Tech Talk today. Again, this fall quarter, we're sort of having the theme of new to ECS, and so we're hiring every year now to keep up with our growing student population, and we were lucky to be able to hire a number of folks last year, which was really great. And one of those was Professor Venkatagiri, who's going to be talking today. And this is particularly exciting. We needed more computer architecture systems faculty, and we were very lucky to convince her to come to Oregon State. She got her PhD at Illinois, and really, I think it's a really interesting research area. I don't have much experience or know much about it, but it seems she's basically coming to terms with the fact that nothing's ever perfect, that there's going to be errors always, and we have to figure out how to deal with them. And so as we were talking about, if you have questions, you can, throughout the talk, you can put them in chat. And otherwise, there'll be time at the end where you can put them in chat or just ask them outright. So without further ado, let's let Radha get started.
Okay, great. Thank you so much, Alan, for that introduction. Hello, everybody. Good morning. Thank you for coming to this talk. So today, I'm going to try to give you a broad overview of the work that I've been doing over several years, in fact, on this topic of democratizing error-efficient computing. Okay. So basically, my worldview is that we live in a world now where errors in computing is becoming ubiquitous and can come from a wide variety of sources, right? And this includes unintentional errors, such as bit flips that happen in your computer hardware, all the way to deliberate approximations and malicious attacks. And traditionally, when people think about errors that are originating in hardware, they think about anomalies in computation that result in anomalous behaviors, such as a blue screen, to something more serious, like changing results of elections, making planes fall from the sky, as well as causing events that can lead to even loss of human life. So naturally, they think about these errors as phenomenon that must absolutely be prevented in a system. And that has traditionally been the view of system designers, in such that they have thrown considerable hardware and software resources at the problem to design systems that prevent all errors, right? That at least attempt to prevent all errors. And this can sometimes include really expensive designs, such as doing a completely redundant and designs in hardware and software in order to protect the user from as many hardware errors as that can possibly be availed of. And the key facilitator for this has been technology innovations that have allowed us to keep adding more and more transistors to our devices while still getting better performance and power each generation. But sadly, this is no longer the case, and designs that aim to prevent all errors in the system are just simply going to be too expensive for a range of future computing systems. But fortunately, the applications that are driving the demand for computing, right? And these could be things like mining, recognition, search, etc., also provide us with new opportunities. And this is because the primary goal of these workloads are not a precise, perfect numerical output, right? And instead, the correctness lies in providing outputs that are reasonably correct, good enough. Rather, they have the right quality of the output in order to ensure that the users have an acceptable experience, right? And this now makes them more tolerant to errors in their computation and data. This has now led to a new class of techniques that now view some errors in these systems as tolerable. So the most interesting example in this kind of error tolerant systems are from the field of low-cost resiliency, where the idea is that some unintentional hardware errors are allowed to escape and corrupt the output as long as they produce user acceptable output. And by doing this, they reduce the overhead for resiliency protection for these hardware. In the last decade or so, though, we've seen another paradigm shift where now we are looking at to actively harness errors to make some desirable system trade-offs. So you may have heard of this line of techniques called inexact computing or approximate computing, where the idea is to replace precise but expensive computation with imprecise but much cheaper computation, right? While still ensuring that the output is still acceptable to the user. So now putting all of these things that we've discussed so far together, right? We must build future systems so that they can reconcile these three different worldviews in order to have systems that can extract the maximum efficiency out of computation while still operating under these different sources of errors. So now we can think about these systems as being error efficient in that they only need to prevent as many errors as absolutely needed while allowing others to occur. And the key idea here is that allowing the system to make controlled errors can conserve resources. Now, these resources could be things like performance, energy, bandwidth, or they could be more abstract quantities such as manufacturing costs, system complexity, etc. Researchers over the last decade and a half have literally published thousands of papers showing the promise of approximate computing, error-efficient computing over different parts of the stack, right? But unfortunately, there has been a lot of resistance to the adoption of error efficiency despite its promise. And this is mainly due to the lack of principled and unified methodologies and the excessive programmer burden that these techniques place. And so the overarching vision of this line of work that I'm going to talk about today is to enable the adoption of error efficiency as a first-class design principle by different users, regardless of expertise, and to do so using methodologies that allow a principled and unified way of computation under different sources of errors. Now, in order to do this, right, what we want to do is we want to start with first principles. And in my book, the most fundamental question that somebody can ask for error-efficient computing is how do errors in a program's execution affect the output of the program? And this is fundamental because once we know this, then we can decide how tolerant an application is to errors, what different kinds of techniques can we do on it, etc. Right. So today, the state of the art, how it is that we rely on program or domain experts to have this really deep understanding of their program's error characteristics. And then we rely on them to then specify these as error specifications in the application that are then used to devise error efficient techniques. Right? And as you can imagine, this is quite limiting because not only is this kind of expertise sparse, it can take years to develop this kind of expertise for any new application or domain. And so the first contribution of this line of work is the development of automated application level error analysis tools that can automatically determine how an error in a program's computation or data is going to impact the final output of the program, right? And the tools and techniques that are developed as part of this work are really the first of their kind that can determine how each single given error, which can span billions across an average size program, is going to impact the output. That is, it determines what is the output that's going to be produced for each of these different kinds of errors, and can do this accurately and at low cost. And now that we have this kind of automated error analysis tools, we can now derive a comprehensive error characteristics of an application, which I'll call the application's error profile for each application that you would want to study. And next, I'll show how the comprehensive error profile that we can derive from this kind of automated error analysis can be used to devise different customized error efficiency solutions spanning a range of techniques, right? From resiliency all the way to approximate computing that can target specific user and application requirements. And finally, the final piece of work that I'll talk about today is how do we make this kind of error analysis more efficient and scalable, right? And to do this, we adapt techniques from the world of software testing to now reason about hardware errors. And this work is also interesting in some way because it integrates the thought process of hardware errors and thinking about error efficiency into the software development framework. Okay, so this work actually spans multiple publications and open source tools. So today, my goal here is to give you a general brief overview of what all of this entails, so that can hopefully spawn some conversations and collaborations down the road. And that's how the talk is outlined. I'm going to be discussing each one of these 3 contributions, and before we talk about some future work. All right. So before I go to the first topic, are there any questions?
I haven't seen any in chat yet, so I think you can just move on.
All right.
Thanks.
Okay, cool. So the first thing we're going to talk about now is the automated application error analysis, right? So what is error analysis? The objective of the error analysis is to understand how errors in a program's execution will impact the final end-to-end output of the program. So to give an example, right, consider the Sobel edge detection application that produces an image output. Now, to understand how a single error in this application is going to impact the output, the best way we know of today is to simply perform an error injection experiment and observe the output. Now, in case of an output corruption, which means that the output you produced did not match the output from an error-free run, what we want is we would like a quality metric that can enable us to compute and quantify the quality degradation in our output. So in this example, the quality metric that we're going to use is the root mean square difference between the between the differences in each pixel across these 2 images. And this tells us that the output that we've gotten has a 7% quality degradation. Now, further, if the user or system gave us a quality threshold, which tells us how much output quality degradation a user or system is willing to tolerate, we can make some more decisions. So for example, in our example here, even though we know that the output is corrupted, we know that the quality degradation is only 7%. And in an example given here, the user is willing to accept a quality degradation of 10%, we know that our output is tolerable since the quality degradation is below this threshold, right? So as you can see, determining what the impact of one error is going to be is relatively simple. But in reality, there are going to be billions of such errors that can impact this program, even for an average sized program, right? Even for a medium sized program. And as you can imagine, doing an error injection experiment in all of these error sites is going to be really, really difficult. And yet the holy grail of error analysis is that we must be able to precisely calculate output quality. That is, we should be able to tell that the quality degradation is 10% versus 5% versus 2.1%. And we should be able to do this for all errors for a given error model, do it in an automated fashion, and also at low cost, right? And bonus points if you can come up with a methodology that's general, that is, it can be applied across a wide variety of applications and error models. Now, meeting all of these requirements is really hard and was a significant research challenge. And in fact, the tools and techniques that I'm going to talk about today in this work are the first of its kind to meet all of these requirements. Now, this error analysis part that I'm going to discuss next spans multiple publications, 4 publications and 3 open source tools. So obviously I'm not going to talk about each of them separately, but there are certain concepts and insights that are common across this. And that's kind of what I want to talk about today. Okay, so before we go further, it's time to define what I mean by an error in this work. So when I talk about an error, I mean any perturbation in program state, that is in its instructions and data, that's caused by an underlying fault in hardware. So underlying fault could be things like electrical noise, high energy particle strikes caused by cosmic radiation, impurities in packaging, etc. Right? Specifically, for error models for the instruction that I'm considering are single bit transient errors in operand registers of dynamic instructions. Now, if you don't know what transient errors are, they're simply errors that are temporary and can be overwritten. And the error model that we'll consider for data are multi-bit, and here I'm talking about random 1, 2, 4, and 8-bit transient errors that can happen in system memory. So taking all of these both of these error models together, the tools that I'm going to talk about can output an application data error profile and an application instruction error profile. Okay, so let's start by looking at the user interface of these error analysis tools. So for input, these tools just need the user to provide an unmodified program that they want to analyze, along with the relevant program inputs, a quality metric, and optionally a quality threshold. And the output of the tool is the application's comprehensive error profile, which is a detailed list of all of the error sites in the program that can encounter the error, as well as the corresponding impact of that error on the final output. Now, to better understand this, let's take a look at one example. So each line in this error profile contains 2 pieces of information. One is the error site description and the error outcome. So the error site describes the location in the program where the error can occur. So for example, considering an error model that has a single bit error in a dynamic instruction, the error site will describe the PC and the cycle, which identifies the unique dynamic instruction, the name of the register and the bit of the register where the error occurred, as well as some additional information regarding register and operand type. The second piece of information, which is the error outcome, details what is the impact on the final output of the program for an error at this particular error site, right? So in this case, for example, we can see that an error at the given error site is going to lead to an output that has a quality degradation of 0.0218%. Okay. Now, similarly, just to give an example from the data error site, for an error model that's considering 1-bit errors in data that's stored in DRAM, the error site will describe the particular data bit at a given location in memory that's going to be read or written by a given dynamic instruction, and accordingly, and the impact of that error on the final output. Now, I want to remind you that what we just saw was one example of this, what's there in this comprehensive error profile. But in reality, there can be billions of such error sites. And as we've already discussed, again, doing error injection in all of these is going to be extremely expensive. But it turns out that we don't really have to do error injection in all of these. And in fact, we can prune the number of errors that need error injection simply by showing some errors to be equivalent to others. Right? And this is coming, so the key insight here, which actually is coming from a long line of resiliency work prior to this work, is that errors that flow through similar control and data paths in the program must behave similarly and hence produce similar outcomes. So the key idea here is that we use program analysis along with certain control and data flow heuristics to identify such errors in the program and show their equivalence. To give you a quick example of what these heuristics that we are talking about, let's just take a quick look at an example. right? So on the screen, you see a toy example where there is a memory instruction in a loop that's accessing a data value at a given location in memory. Now, the objective of the error analysis is to answer the question, what happens to the output of the program when there are errors in this particular data value, right? That's the overarching error analysis question that we're asking. Now, given two dynamic instances of this memory instruction, the static memory instruction, the equivalence question now we are asking is, will errors in data value X and Y that are being accessed by these two different dynamic instances impact the output of the program in the same way? And in order to understand that, we want to capture how errors in these two data values flow through the program. And so the equivalence heuristic that we're going to use here is to observe subsequent instructions in the program that read and propagate these erroneous values, and then build an ordered list of such loads till we see a write to the corrupted value. And then and if both of these load chains are equal, then we say that errors in X and Y are going to be our equivalent. Now, of course, this kind of equivalence heuristics heavily depends on the data model. So for example, if you have the errors not happening in the data, but actually happening in the instruction itself, for example, in the registers, then the heuristic that we use will be different, right? So for example, we use, I'm not going to go into details, but we use a control flow heuristic in this case to capture the propagation of errors in registers. Okay, so now using this kind of program analysis and heuristics, what the tools do is that they identify and group similar errors in the program or equivalent errors in the program into these equivalence classes. Then from these equivalence classes, we can just select one representative error, which I call a pilot, and then do an error injection experiment on the pilot and observe its outcome. And then we can say that the outcome of the pilot is representative of the outcome of all of the errors within its equivalence class. And hence, using this kind of error pruning, we now just need a few error injections to predict the outcomes of virtually all errors within a given program. Okay, and we have shown that these kind of pruning is very effective, and we can reduce the number of errors that we need to analyze by expensive error injections by up to 5 orders of magnitude. Are there any questions, Alan, before I move forward? In the chat? Or anybody want to ask?
Yet. None yet. No, I guess
okay, all right.
Very clear.
Okay, good. Okay, so because we're using heuristics now to build these equivalence classes, we need to test them and make sure that the heuristics we're using are correct. So the question that we want to ask is, do the pilots accurately represent their respective equivalence class? And in order to do this, we do validation experiments. So what we do is we simply take a random number of sample errors from a given equivalence class, I call it the population, and perform error injection experiments on them. And then we observe the degree to which the outcomes of the pilot and the population match, and then assign them an accuracy score. And in order to build a confidence in this technique, we do this kind of validation across a wide range of equivalence classes, error models, applications, etc. And overall, we do around 7 million error injection experiments to validate that this technique is correct. And just to show you a quick example, right? The graph on your screen is showing the validation accuracy on the y-axis for the 1-bit data error model across a few different applications. And as you can see, the average accuracy is pretty high. It's around 97%. And we noticed that this trend continues across the different error models, right, of the 2-bit, 4-bit, and 8-bit error models. And as I mentioned, we do this kind of validation accuracy across the different variable parameters here and observe similar validation accuracy. Okay, so now that, hopefully I've shown you how we do the error analysis and how we produce the application's comprehensive error profile, I want to run through a few quick examples of how we can use these error profiles now to enable customized error efficiency solutions that can target either the user or the program requirements. So the first example that I want to show you, a quick time check, okay. So the first example that I want to show you here is targeting a use case of low-cost resiliency. So here we're going to take the instruction error profile and devise a customized low-cost resiliency solution for the application. So the idea here is very simple. We want to identify and selectively protect those instructions in the program that lead to an unacceptable output corruption in the presence of errors. And the protection scheme that we're going to use here is instruction duplication, which is simply saying that run each protected instruction twice and then observe the outcome. So obviously this is like pretty heavy. So the less number of instructions that we actually need to protect, the lower the overhead of the scheme. Now, given additional criteria, such as resiliency coverage, which is asking what is the fraction of errors that the user wants to protect against, an optimizer can pick the right set of instructions that balances the required quality versus resiliency coverage versus overhead requirements for the user or system. Right. So, for example, the curve that you see on your screen is for this application called water, and the y-axis is showing the overhead, x-axis is showing the resiliency coverage, and this is the curve that you would get if the user was not willing to tolerate any loss in output quality. Right. However, if the user was willing to accept a quality loss of just 1%, then we show that significant resiliency overhead savings of 55% is achievable while still maintaining a really high resiliency coverage of 99%. So this is a kind of tailoring, automatic tailoring that you can now do to satisfy the requirements that you may have. Any questions so far? Okay. All right. So to just show you the versatility of this approach, right, I want to show you another example. And this time, the use case that we're going to do is we're going to now take the data error profile. Last time we used the instruction error profile. Now we're doing the data error profile, and now we're going to use a whole different technique. We're going to use an approximate computing technique here. And the idea here is that first we want to identify the first order approximable data in the program and then apply an approximate computing technique to it, right? So first let me show you how we identify approximable data in the program. So the graph in front of you is showing the percentage of data bytes in an application. And this particular application we're looking at is FFT on the y-axis, and on the x-axis we are showing approximation target. So the approximation target is simply asking, so for example, for the 90% approximate target, what this is showing us is what are the number of data bytes in the application that are approximable, which means they produce acceptable outputs for 90% of the single bit errors that they encounter. Right now we're talking about single bit errors. So in this case, we see that in this particular application FFT, 77% of data bytes are approximable 90% of the times when they're corrupted with a single bit error. Now, obviously, this will change depending on the error model. So for the same application, while 77% of data bytes were approximable under the 1-bit model, which was the blue line, we can see that this reduces quickly to 0% for the 8-bit error models. Now, of course, how tolerant an application is to data is heavily workload specific, which is sort of why we are doing this, right? Why it's important to devise customized error efficiency solutions. And to just show that, here I've shown you those same 4 bytes versus approximation target lines for a different application, and this application is called swaptions. And as you can see here, this 90% of the data bytes are approximable across the range of error models for this application. Okay, so now that we've seen how to identify these approximable bytes, just to complete this example, let's apply a approximation technique to this model. So the approximation memory technique that I'm going to talk about here is lowering DRAM refresh rate of your of the DRAM in order to save some power, right? And I'll explain what this means. So the simple idea here is that you take the application data and you divide it into critical and non-critical data. So critical just means that you cannot tolerate any errors in them, and non-critical is data bytes that produce approximable errors. And you divide them into critical and non-critical data, and then store them in different banks of the DRAM that are then going to be refreshed at a different rate. So critical data is going to be refreshed at the normal refresh rate, and non-critical data is going to be refreshed at a lower rate, which will save you power, but at the cost of inducing modest errors in the DRAM. Now, in the original technique, you needed a programmer to identify and do this partitioning of critical and non-critical data for you. But now, using automated error analysis, we can automatically identify which data is critical and which data is non-critical and do this partitioning. So for an example, for the swaptions application that we saw, given a quality threshold, we see that we can do the automatic mapping that we produce is accurate, 99.9% of the times over hundreds of thousands of application runs, and produces a power savings of, on average, 23%. Okay, so hopefully what I've shown you so far is how we can do the first two parts, how we do the automated application of error analysis, and how that can then be used to devise customized error efficiency solutions. Do a time check. Okay, so we are at 11:36. So I'm just going to go over any questions so far.
No, I think you're good to go on.
Okay, great. All right. So the last piece of this, and I'm just going to go quickly because I want to stop in a few minutes to see if there's any discussion points here. But so the last piece now then is, so we know how to do this application level error analysis, but even though we have reduced the number of errors that we need to do error injection on by many orders of magnitude, it still requires error injection in some parts of the program, right? In some error sites, and that can still be expensive. So what we want to do next is we want to make sure that we improve the efficiency and scalability of error analysis even further. And in this last piece of work, it's the basic concept insight here is that analyzing a piece of software for errors is analogous to analyzing it for software bugs. So I should say hardware errors here, right? Hardware errors is equivalent to analyzing it for software bugs. And so the main idea is to leverage techniques from the world of software testing to improve error analysis. And we come up with a framework called Minotaur that adapts 4 software testing techniques to error analysis. And just going by it quickly, right? So the first technique that we use is simply to devise a criteria of quality for the input. And we show that we can just look at we can just use a criteria of static instructions at the object code and use that coverage to understand, whether the input that's exciting these is of sufficient quality or not to proceed with the error analysis. And the second technique that we use is it's called test case minimization in the world of software testing. And we use that to build high quality and fast to minimize inputs from slow standard inputs. The idea here is that doing an error analysis over a smaller input is going to be much faster. And the third technique that we use is from test prioritization from the world of software testing, where we prioritize analyzing specific parts of the program based on the analysis objective, and then terminate the analysis early when that objective is met. So to give you an example, if, from what we had seen a few slides earlier, if the objective of our program, of our analysis, was to identify particular static instructions in the program that produce unacceptable outputs, then we will first prioritize analyzing those parts of the program that we think will lead to unacceptable outputs. So for example, in instruction, you can first try analyzing errors in high order bits of the instruction. And then when you see that, and then you can terminate, when you find a bit that leads to an unacceptable output, you can stop analyzing that particular instruction and then just put it into a bucket of an instruction that produces an unacceptable output. Finally, we prioritize analysis over fast, potentially inaccurate inputs first, and then hierarchically build accuracy by analyzing slower, more accurate inputs later. So, that was just that was a very quick overview, but doing all of these, putting all of these techniques together, we see that we can get almost a 4x average speed up in error analysis. And if you use these techniques towards particular objectives, for example, targeting resiliency or approximate computing, these speed ups can be pretty high. And we've observed up to 55x speed up in the error analysis itself. Okay, so check. All right. So far, I've given you a pretty broad overview of this line of work, where we started with taking an application without needing a program expertise, doing automated application level error analysis on it. I've shown you how we can use these to devise customized error efficiency solutions that can target specific user requirements and can scale different techniques. And then I've also shown you the last piece of work, which was how do we actually use software testing techniques to improve the efficiency and scalability of the error analysis. Okay, so what's next, right? What do we want to, what is it that I'm working on now, and rather what I want to do? And hopefully, we can have some ideas and topics for collaboration on this, right? So ideally, to have an independent error efficiency stack, what you need is full stack solutions, right? That can go from application to all the way to error efficiency solutions. So even though the work that I've described so far gives us a proof of concept of how this can be done, in the real world, in order to do this, we really need techniques across different layers of the stack. And researchers have been making progress at different layers of the stack to do this kind of error efficiency. But what we're really missing are the abstractions that can integrate all of these things together to form a full stack. And doing that has implications on all of these different core disciplines, right? So for example, one of the questions that we can immediately ask following this line of work is, what are the right metrics that we need to extract information about an application's error tolerance from its error profile, right? And then how can those be used to abstract and then provide error specifications to a programming language, for example? How will the compiler use them? And what are the knobs that you need in the hardware and the compilers so they can talk to each other and do actually apply some of the error efficiency techniques? So a lot of questions on that end. The other dimension that we can look at is error analysis, and so I should say comprehensive error analysis, right? The kind that I've been talking about, where you can determine, so you can say what the output is going to be for every error the program can encounter. It's really hard, right? And so far, what I've shown is how we can do this for single-threaded CPU kind of workloads. But what I'm interested in also is, can we scale this to larger distributed applications, right? So like autonomous vehicles, computer vision, robotics, edge computing applications, etc. How can we scale them to these kind of applications? And these are very natural candidates for error efficiency because they deal with a lot of sensory data. audio, video, etc. And so they're naturally good fits for error efficient computing. The third quadrant that I want to talk about is the use cases for error efficiency. So I've shown some use cases for hardware resiliency and approximate computing, but you can think about this kind of error efficiency for other types of techniques that deal with anomalies in computation, right? So for example, how do we efficiently protect against fault attacks? Or how do we, can we use them to find, can we use this kind of analysis to find bugs during hardware validation? What about criticality testing for emerging storage solutions, right? So these are just some of the few examples that that I'm interested in exploring, and hopefully it's food for thought for others here as well. And finally, and this is kind of like a long spanning project, right? Ultimately, what we want is system-wide solutions. So what we want to be able to do is take a system that has heterogeneous sources of errors. You have like your networks, you have your hardware, you have your software, and we want to be able to build a system that can integrate the integrate error efficiency across all of these different individual parts, and then build one integrated solution for the entire system. And this is hard because there's a lot of different types of work here. So you have to think about error models, you have to think about the different error efficiency for the different parts of the system, and how do they interact with each other? Do they compose? Do they negate each other, etc.? Lots of interesting questions in this space. So so basically, the final thought on this is that I think error efficiency is a very exciting field. Lots of important questions that require a lot of hard science and lots of opportunities for collaboration. And I think future in this area is pretty exciting. Oh, we're on 46. Okay, so with that, I want to acknowledge a lot of my collaborators and funding agencies. And with that, I want to thank you for your attention, and I'm happy to take any questions.
Thanks a lot. That was interesting.
Thank you.
I wonder, yeah. So are there, I have some questions, but I want to give other people a chance if they have anything immediately. Otherwise, I'll just jump right in. Yeah, so I'll get us started. So it was this is more of a technical thing. So I was just curious. The FFT program seemed to be more sensitive than any other. It seemed to be the most sensitive of your benchmarks. FFT.
Yeah.
From what I remember in the graphs, was that due to something fundamental about the program and how it differed from the others, or how you're measuring error? What was that a result of?
It's actually both, but the fundamental reason is actually the program itself and how it's using the error, So FFT is a very mathematical program, right? So it's it's very easy for errors in any kind of data or computation to show up in the final output. For the other sort of application that I showed, I think I showed swaptions and water were the other applications. These are more HPC applications. The swaption is doing like a Monte Carlo analysis. So it's easier for errors to be masked in these kind of programs. So I would say the difference that you're seeing very largely is the inherent nature of the application itself. And the second thing that you brought up, I didn't really talk about it, but that's an interesting point also. How we measure the output corruption, and this goes back to the quality metric that I was talking about earlier. So if you remember, we had 2 images, and then I used like root mean squared error to compare them. That the quality metric, that determines also what the output corruption is. Now, I could have used like signal to noise ratio, for example, as a different quality metric to measure the output, and that perhaps would have changed would have changed the error profile a little bit.
Mhm.
But that's a secondary effect. The primary reason why you've noticed this kind of changes is mainly the application and what it's doing with the data.
Right.
Which is why, some applications are more amenable to this kind of error efficient computing than others are. It's just very application specific.
Yeah. It certainly seems like a lot of the perceptual data applications will be really amenable to this.
Yeah, and it's really important not only to know how much the output quality is varying, but it's important to know which are the errors that cause that variation, right? So you have to do controlled errors, which is why this error analysis is so important to do to begin with.
Does anybody else want to unmute and ask a question or put something in chat?
Either I was very clear or I was not clear at all.
Yeah. I thought it was very clear.
Okay.
I've got a number of questions just to hear what you think about
Sure.
how you're thinking about this.
Let me stop sharing so I can.
Yeah.
Okay.
I mean, one thing that came to my mind when I was thinking about errors and real applications is a lot of times we use compression, for example, to save space. Right? We compress most images, but compressed data is going to be more finicky about errors than uncompressed data. Is that so? A bit error in a compressed file is going to possibly be more damaging than if it's in the uncompressed file. Is that something that comes up? It seems like there's some sort of a trade-off there. Compression ratios versus error tolerance in memory. I don't know if people look at that sort of thing.
No, I don't think people have really done error analysis. I mean, I'm sure people have looked at, what is the, for lossy compression, what the ratio is, and device techniques, approximate techniques around it. But your point is interesting, so the error analysis for compressed data is, I would imagine is going to require a fundamentally different error model and different heuristics than doing this kind of analysis for non-compressed data. Just because an error so the first thing we think about, like you just said, right, is that an error can potentially have a larger impact on compressed data. But the thing that we probably also need to look at is, how does this error propagate in the compressed and uncompressed data within a program, right? If it's the same, does it need different heuristics, et cetera? So so the easy answer to your question is yes, that it's definitely probably going to need different analysis techniques, and has not been done yet, the error analysis itself. And it probably needs different heuristics, or at least modified heuristics to deal with compressed data.
Yeah. And then I was kind of curious. So you mentioned basically for this type of analysis to be really useful at the end of the day, besides just understanding the error profile, we want computing hardware and mechanisms for trading off something for errors, power for errors, like you get a trade-off there. And you mentioned the refresh rate, that was one way. I've seen Tejavi mention something in wireline communications. He can trade off power for error rate. What other opportunities do you see, in hardware or software land for that type of trade-off? And is it always energy, or is there something else that we're?
No, it could be energy. It can be things. Energy is one. Performance is another. You want your program to finish fast. So a classic technique that people use in software, for example, is just it's called like task dropping. So you can just like, you can analyze the program, understand how the program behaves, and then find out which tasks are more critical and which tasks are not. And you can just, so let me give you, a task is a very broad word, right? So one example I can give you is say, this technique called loop perforation. So if you have a loop that's, running for n iterations, you can choose a threshold and say that I'm going to skip every other iteration, for example. So that's a performance technique, right? You want your program to run faster. People do this kind of stuff. I gave you an example for resiliency overhead, right? So it's not, so you're not trading, the resource you're trading off is not energy or power, but you're saying, okay, how I want to protect this program in such a way that it's still acceptable if I have errors, but I want my overhead of the resilience to be quite low. People have done this kind of thing, approximate computing techniques for reducing complexity in the program, for example. You can do this for, improving yield of your hardware. So if you have a hardware that has a lot of faulty memory cells, for example, right? You can still use them, but you intelligently map your data such that the critical parts are not on the faulty hardware; they're on correct hardware, and the non-critical portions can be mapped to faulty hardware. So that's an example of improving yield. So there are many different factors that you can optimize for. Doesn't just have to be energy.
Yeah, that's interesting. Is there a market these days for? So when you buy a nail, or a screw, you can get a quality measure of that screw, various different ones. And for processors, is there a wide variance of what people will sell in terms of error rates?
I mean, no, not as fine-grained as error rates, but it's more coarse-grained, right? So Intel will sell a part that has that's working perfectly, for example, for banking applications. But if you're in your PC, you may not get a part that's completely fully functional, right? But people, and this is what I was talking about earlier. So if you look at a data center, for example, a lot of resources put into making sure that even though you're using faulty hardware, your overall application doesn't see these faults. So typically, IBM, this is a good, so IBM in its hardware uses anywhere from 15 to 20% overhead just in hardware to provide techniques. So they'll do things like, I don't want to get into too many things, but they'll do things like, they'll shadow faulty flip-flops, for example, or have like ECC protection or chip kill protection, etc., to mask the fact that the hardware has errors from the software, from the ultimate user. So this can span anywhere from 10% to 25%, and it's not sustainable. Right? It used to be sustainable earlier because we had more slots, so we could just keep adding more and more protection. But it's not feasible as we go forward. 25% on exascale, data centers is going to, exascale computing, is going to be too much as you build bigger and bigger systems. And on the flip side, for really tiny systems, right, that live on the edge, they cannot afford these kind of overheads. So then you have to devise techniques where, you need to live without the ECC, for example, or live with these faulty commodity parts that are going to fail in the field probably. So it's, yeah. That's a really long answer to your question, Alan. Hopefully I gave you some insight.
It's useful. It just seems like, there's interesting market opportunities for your cheap foundries, I guess, in the future. Yeah. Okay. Well, thanks a lot. I think, we're pretty much at the end of the hour. So thanks again, Radha. And anybody who is watching this video or is still here and would like to contact Radha, I'm sure she's an email away. She'd be eager to talk to you about this work. So thanks a lot, everybody. We'll be back in 2 weeks.
Thank you. Bye.